Now here's a more complicated situation. We've got an electron being fired through parallel plates, but it's being fired through horizontally, perpendicular to the field. Okay, so the field is still going to affect it in a vertical manner, but now it's also traveling horizontally. So we're going to have to use some vectors here in order to figure out what is the change. So this is really what's happening in an old CRT television, cathode ray tube. So an electron gun fires electrons through a parallel plate space, and it's deflected somehow, either upward or downward somewhere, to the correct position on the screen. And when it hits the screen, it lights up a pixel in the correct color. So this isn't really technology that we often use anymore, but it was very important in its time. So first, we're going to figure out the length of time the electron is between the plates, because that's the amount of time it's being affected by the field. Okay, and in this case, it's going to be between the plates for this 5 centimeters, and then it'll be gone, and it won't be affected by the field anymore. So we just actually need to use the x direction. We don't need to know anything about the y direction to know how long it's between the plates. Okay, so we're going to use the x direction only and to figure out the time. So remember that velocity is displacement divided by time. And so if we're calculating time, time is equal to displacement divided by velocity. These are vectors. Okay, and so now the time is going to be equal to that 5 centimeters, or 0.05 meters, divided by the velocity it has going through the plates. Now we can just use that initial velocity, that 1.5 times 10 to the 4, because its horizontal velocity is not at all affected by the field. Only its vertical velocity is affected by the field. So we can just use 1.5 times 10 to the 4 meters per second. And when we do that, we get 3.3 times 10 to the negative 6 seconds. It's only between those plates for a very tiny amount of time, so it's probably not going to change distance or change vertical position a whole lot unless that field is massively strong. And since this is only one electron, it has a tiny amount of charge, we can expect a very little difference in vertical position. Okay, so we're going to now look for the displacement in the y direction while between the plates. So here we go. This section is the one that's complicated. So we're looking for what is the y displacement. Okay, and in order to figure that out, we need to know what the acceleration is in the y direction. Okay, if we knew the y acceleration, we know the initial velocity, vertical velocity, is 0. We know the amount of time it's between the plates. So if we knew the acceleration, we could figure out that displacement. Okay, so that's really what we're going to shoot for. How do we figure out the acceleration of this thing? So here we go. To figure out the acceleration, we're going to need to use F net equals ma. Okay, we don't have acceleration anywhere else other than in kinematics formulas, but we don't have enough kinematics information to figure out the acceleration that way. So we're going to have to figure it out using a different method. Okay, the force it's experiencing is the electric force, Fe. Okay, Fe is charge times field strength. Now, we still don't have field strength. We have charge and we have mass, but we don't have the field strength to figure out the acceleration. But we do know that field strength is also equal to voltage divided by distance, or divided by separation. So Q times change in V, voltage that is, divided by change in d is equal to ma. Okay, now we actually have all these things. We have the charge, it's 1 electron. We have the voltage between the two plates. We have the separation of the plates, and we have the mass of an electron. So that allows us to solve for the acceleration. The acceleration is going to be q times change in v divided by m times change in d. So our q is 1.6 times 10 to the negative 19 coulombs. Our v is that 1.85 times 10 to the negative 16 volts. Our mass is 9.11 times 10 to the negative 31 kilograms, and our displacement is 0.05 meters. And when you do all of that, you get an acceleration of 6.49 times 10 to the negative 4 meters per second squared. Okay, this is the part that it's difficult to figure out how do I get there, right? Sometimes when you're solving a problem, there's a way to get there, but figuring it out, what's the path, that's the difficult part. So we have to think about what formula could I use to find this piece of information, and then how do I trace that back to what I do have? Okay, so I know the initial vertical velocity. I'm looking for the final vertical velocity down here so that I can figure out the displacement. There's other ways, but in order to get there, I have to have the acceleration. Now, let's take stock of what we have now. We have the acceleration, we have the initial vertical velocity, we have the time. And if you look through your kinematics formulas, you'll find that you can figure out the y displacement with this formula. v1 change in t plus half a change in t squared. Okay, we have initial velocity, that's just 0. We have the acceleration now, and we have the change in time. And so now we can solve for this y displacement. So this y displacement is going to be equal to half times 6.49 times 10 to the negative 4 meters per second squared times that time that it was between the plates, which is 3.3 times 10 to the negative 6. That's squared, and when we multiply that out, we get a y displacement of 3.5 times 10 to the negative 15 meters. That's a very small distance, which we expected. Now, a displacement has a direction. It's a vector. So we need to figure out what is the direction that it moved in. So according to our diagram above, the positive plate is on the top, the negative plate's on the bottom, and so this electron is going to be pushed upward. It's going to deflect upward. Okay, so that's going to be our direction for the y displacement. Up. And finally, we're going to figure out the total final velocity of the electron. So now we have a whole bunch of information. We have the distance it traveled in the y direction, we have its y acceleration, we have the time that it was between the plates, we have the initial velocity. So probably the easiest way to figure this out would be going like this. v2y is equal to v1y plus a change in t. There are other ways, but this is probably the most straightforward. So now we're going to just solve for v2y, because we know that v1y is 0. We know the acceleration is 6.49 times 10 to the negative 4 meters per second squared. And we know that the time is 3.3 times 10 to the negative 6 seconds. So we're just going to multiply these two things, and we end up with v2y is equal to 2.14 times 10 to the negative 9 meters per second, and that's in the upward direction. Okay, now it's not quite as simple as that, because it had horizontal velocity to start with as well. So we're going to need to take the x horizontal velocity vector and the y vertical velocity vector and put them together. We've done this a whole bunch of times though, so hopefully this is okay. Here is the horizontal velocity, which was 1.5 times 10 to the 4 meters per second. Here's the vertical velocity. I'm not going to draw this to scale because it is negligible, really. So this is 1.5 times 10 to the 4, 15,000 meters per second, and this is 2.14 times 10 to the negative 9. It's so small, it's not really going to make a difference in the end. Okay, but here's our resultant. Again, grossly exaggerated. And this resultant is really what we're going for. What's V2 total? Okay, so V2 total is going to be the square root of these two things squared, right? Pythagorean theorem. So V2 is equal to the square root of 1.5 times 10 to the 4 squared plus 2.14 times 10 to the negative 9 also squared. Okay, now when you do this, you're going to find, just like we said, that this vertical velocity is really just negligible, and so your final velocity is going to be 1.5 times 10 to the 4 meters per second. Now, that also means that the angle is negligible. This angle in here, we need to give this a direction. So we're going to find that if you do the inverse tan of 2.14 times 10 to the negative 9 divided by 1.5 times 10 to the 4, you're going to find that this distance being so small will give you basically a zero angle, right? But if you actually do it in your calculator, you will get 8.2 times 10 to the negative 12 degrees above horizontal. That's negligible. Okay, so we've got our final velocity here, 1.5 times 10 to the 4 meters per second. Not every question are you going to find that the vertical velocity is also negligible, but you need to be able to follow through all these steps to get it.